Imagine this moment. You're standing beneath a star-filled sky, wondering about the mysteries that dwell in the cosmic depths above. The countless points of light stretching across the heavens represent a vast cosmos filled with worlds beyond imagination, each one telling its own story of cosmic evolution and planetary formation. Among those distant lights lies something extraordinary: Jupiter. But here's what will shatter every assumption you hold about planets. There is no ground to stand on. Jupiter possesses no solid surface whatsoever. This fundamental difference between Jupiter and the terrestrial worlds we're familiar with reflects a completely different pathway of planetary formation. While Earth, Mars, Venus, and Mercury formed through the gradual accumulation of rocky materials that eventually created solid, differentiated worlds with distinct crusts, mantles, and cores, Jupiter represents an entirely different evolutionary history. Jupiter formed in the outer reaches of our solar system, where temperatures were cold enough for water and other volatile compounds to freeze into solid ice. This allowed the planet's core to grow rapidly by accreting both rocky materials and frozen volatiles, eventually reaching a critical mass that triggered a period of runaway gas accretion from the surrounding solar nebula. The result is a world that's more like a miniature star than a planet in the traditional sense. Jupiter's composition, roughly 90% hydrogen and 10% helium, closely matches that of the Sun itself. The only reason Jupiter didn't become a star is that it never quite achieved the mass necessary to ignite nuclear fusion in its core. If it had grown to about 80 times its current mass, Jupiter would have become a second sun, fundamentally altering the character of our entire solar system. Should such a surface magically exist, the crushing gravitational forces would compress you instantaneously into something thinner than the finest paper. Jupiter's immense mass creates a gravitational field that is approximately 2.5 times stronger than Earth's, at the level where atmospheric pressure equals Earth's sea level pressure. But this comparison understates the true extremes you would face trying to approach Jupiter. The atmospheric pressure increases rapidly as you descend toward Jupiter's core. At depths where the pressure reaches just 10 times Earth's atmospheric pressure, you would already be experiencing conditions more extreme than those found at the bottom of Earth's deepest ocean trenches. Continue deeper, and the pressure continues to mount relentlessly. Thousands of miles below Jupiter's visible cloud tops, the pressure becomes so intense that hydrogen itself undergoes a dramatic transformation, changing from a gas to a liquid to an exotic metallic state that doesn't exist naturally anywhere on Earth. This metallic hydrogen ocean extends for thousands of miles through Jupiter's interior, creating the most extreme material conditions found anywhere in our solar system. Yet this revelation merely scratches the surface of Jupiter's bewildering reality. The planet exists at a fascinating boundary between worlds and stars, embodying characteristics of both while fully belonging to neither category. Jupiter challenges our attempts to neatly categorize celestial objects, representing a fundamental type of world that may be among the most common in our galaxy. Tonight, we embark on an exploration into one of space's most compelling mysteries, the true magnitude of Jupiter's mass. We're speaking of incomprehensible enormity here. Consider a world so colossal that it redefines everything we understand about planetary objects. This cosmic behemoth resembles a stellar failure more than any rocky world familiar to us. Should you ever feel insignificant beneath the stellar canopy, prepare yourself. Grasping Jupiter's authentic scale will humble you beyond imagination. This gas giant prowls our solar system's outer territories like some ancient guardian. While we prepare for this cosmic journey, I'm curious about your earthly location tonight. Share where you're joining this exploration in the comments. Something profoundly moving exists in contemplating Jupiter's vastness, while we remain scattered across our tiny blue world. Additionally, your support through subscriptions or engagement would be deeply appreciated. It truly matters to me. Our journey begins now. Let's perform a thought experiment. Visualize Earth completely. Every ocean, continent, mountain range, and bustling city. Hold that mental image firmly. Now imagine Jupiter as an enormous cosmic pumpkin, completely hollowed out. How many Earth-sized spheres could fit within that colossal shell? Venture a guess. Perhaps 100. 500. The reality surpasses imagination. Over 1,300 Earth-sized planets could nestle inside Jupiter with space remaining. But here's where this becomes even more astounding. Despite accommodating over 1,000 Earths, Jupiter consists almost entirely of the universe's lightest materials, hydrogen and helium, identical elements that power our Sun. This transcends typical astronomical presentations filled with mere statistics and numbers. We're investigating how Jupiter's enormous scale sculpted our entire solar system, influenced Earth's life-supporting conditions, and continues serving as our cosmic protector. We'll explore recent revelations suggesting Jupiter once exceeded its current dimensions, possibly doubling in size, wielding magnetic forces that defy comprehension. By our journey's conclusion, you'll recognize Jupiter not merely as our solar system's largest planet, but as the fundamental reason our cosmic neighborhood exists as it does. This heavyweight champion wielded its massive influence during our solar system's early formation, dictating planetary formation locations and restrictions. Jupiter possesses such incredible mass that it actually causes our Sun to wobble. Let's establish foundational understanding, because even Jupiter's basic characteristics prove absolutely staggering. Discussing Jupiter's dimensions means examining something far beyond somewhat larger than Earth. We're contemplating scales so immense they obliterate conventional planetary concepts. Jupiter's equatorial diameter spans approximately 88,846 miles. For perspective, 11 Earths arranged side by side would barely span Jupiter's width. The fascinating complexity deepens here. Jupiter lacks perfect spherical form because this massive world rotates incredibly rapidly, completing full rotations in under 10 hours. This creates polar flattening and equatorial bulging. Nearly 6,000 miles separate Jupiter's equatorial and polar diameters, equivalent to the distance spanning from New York to London. Jupiter literally stretches itself out of shape through its own rapid spinning. Contemplate this momentarily. This world is so enormous that the difference between its equatorial and polar measurements equals crossing Earth's entire Atlantic Ocean. This dimensional variance exists because Jupiter spins so rapidly that centrifugal forces actually combat the planet's massive gravity, reshaping the entire planetary body. Now, if Jupiter's diameter measures 11 times Earth's size, you might assume its volume would also be 11 times larger. However, three-dimensional space doesn't function that way. Scaling up in 3 dimensions means volume increases by the cube of linear scaling. Therefore, Jupiter's volume actually measures 1,121 times larger than Earth's. Let me provide a visualization aid. If Earth resembled a grape's size, Jupiter would match a basketball's dimensions. Yet even this comparison fails to capture the reality we're confronting here. When discussing Jupiter, we're not merely addressing size, we're examining mass. And Jupiter's mass ventures into truly extraordinary territory. Jupiter weighs approximately 318 times Earth's mass. Here's the stunning revelation, combining every other solar system planet, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, plus all their moons, into one superplanet. Jupiter would still possess 2.5 times greater mass. Allow me to emphasize this point. Jupiter alone contains more than twice the mass of everything else orbiting our Sun, excluding the Sun itself. This incredible mass concentration occurred during our solar system's early formation, approximately 4.6 billion years ago, when our cosmic neighborhood consisted of swirling gas and dust surrounding our newborn star. Jupiter originated as a solid core composed of rock and ice in outer regions, where temperatures allowed these materials to condense. Once that core achieved critical mass, somewhere between 10 to 20 Earth masses, something remarkable occurred. Jupiter initiated what scientists term runaway gas accretion. The planet began consuming hydrogen and helium directly from the solar nebula at tremendous rates. Within mere millions of years, Jupiter achieved roughly its current size, capturing most remaining material in the outer solar system. This process operated so efficiently and completely that Jupiter essentially starved the remaining outer solar system of construction materials. This explains Mars's smaller size compared to Earth, and why the asteroid belt between Mars and Jupiter never coalesced into a planet. Jupiter arrived first and consumed everything. Jupiter's mass transcends impressive numerical statistics. It produces real, measurable effects we can observe today. Jupiter's gravitational force is so powerful, it actually influences our Sun's orbit. Yes, the Sun doesn't remain perfectly stationary at our solar system's center. Instead, it wobbles slightly as Jupiter orbits around it. The gravitational interaction between these massive objects creates a common mass center called a barycenter, which actually lies outside the Sun's surface. This solar wobble caused by Jupiter proves so significant that astronomers employ it as a technique for discovering planets around distant stars. When they observe stars wobbling in regular patterns, they recognize the likely presence of massive planets, probably resembling Jupiter, orbiting those stars. Jupiter's gravitational influence extends far beyond making our Sun dance. The planet functions like a cosmic vacuum cleaner, protecting the inner solar system from potentially dangerous asteroids and comets. When these objects hurtle inward from the outer solar system, many become captured by Jupiter's gravity or flung into interstellar space. Without Jupiter's protective presence, Earth would suffer bombardment from far more potentially extinction-causing impacts. The asteroid belt itself testifies to Jupiter's gravitational dominance. Instead of forming into a planet, rocky debris between Mars and Jupiter remains scattered in a belt because Jupiter's gravity prevents coalescence. Jupiter's influence creates gaps in the asteroid belt called Kirkwood gaps, where gravitational resonances have cleared material over millions of years. Here's something that might surprise you. Despite Jupiter's enormous mass, it's actually less dense than water. Jupiter possesses a density of only 1.33 grams per cubic centimetre, compared to Earth's 5.5 grams per cubic centimetre. This low density reveals something crucial about Jupiter's composition. The planet consists primarily of the universe's lightest elements. Approximately 90% of Jupiter's atmosphere is hydrogen, with most of the remaining 10% being helium. These represent the same elements that fuel nuclear fusion in stars. Indeed, Jupiter contains essentially identical basic ingredients as our Sun. The sole difference: Jupiter never achieved the mass necessary to ignite nuclear fusion and become a star. Some scientists reference Jupiter as a failed star, and truth resides in that description. Had Jupiter been roughly 80 times more massive, it would have possessed sufficient gravitational pressure in its core to begin fusing hydrogen into helium. Instead of orbiting in our solar system, it would have become a second sun, making our cosmic neighborhood a binary star system. This raises fascinating what-if scenarios. What if Jupiter had managed to accumulate slightly more mass during formation? Our solar system would appear completely different. Earth might not exist at all, or if it did, it would be a vastly different world with two suns illuminating its sky. Jupiter's internal structure proves as alien as its size is impressive. Descending through Jupiter's atmosphere, hydrogen gradually becomes increasingly compressed. About 1/3 of the way down, something extraordinary occurs. Hydrogen becomes so compressed that it transforms into a metallic state. This metallic hydrogen doesn't exist naturally anywhere on Earth. We can only create tiny amounts under laboratory conditions for microseconds at a time. Inside Jupiter, this metallic hydrogen exists in vast quantities, forming what might be our solar system's largest ocean, not water, but liquid metal. This metallic hydrogen ocean extends for thousands of miles through Jupiter's interior. This metallic hydrogen ocean generates one of Jupiter's most impressive features, its magnetic field. As Jupiter spins rapidly on its axis, this conducting metallic hydrogen creates currents that generate an electromagnetic field approximately 20,000 times stronger than Earth's magnetic field. Jupiter's magnetosphere scale, this space region dominated by its magnetic field, proves truly staggering. It extends millions of miles in all directions, reaching almost to Saturn's orbit on the Sun's opposite side. If you could observe Jupiter's magnetosphere with naked eyes, it would appear several times larger than the full moon in Earth's sky. This massive magnetosphere traps and accelerates charged particles to incredible energies, creating radiation belts millions of times more intense than Earth's Van Allen belts. The radiation environment surrounding Jupiter is so harsh, it poses serious challenges for visiting spacecraft. Electronics on these spacecraft require special hardening to survive even brief exposures to Jupiter's radiation. The interaction between Jupiter's powerful magnetosphere and its moons creates some of our solar system's most spectacular phenomena. Io, orbiting deep within Jupiter's radiation belts, experiences tidal forces so intense they heat its interior and drive constant volcanic activity. The electrical current flowing between Jupiter and Io generates more power than all Earth's power plants combined. Recent Jupiter missions have revealed that the planet's size and structure exceed our previous understanding's complexity. NASA's Juno spacecraft orbiting Jupiter since 2016 has provided unprecedented insights into the giant planet's interior. Data suggests Jupiter's core might be larger and more diffused than scientists expected, extending over a significant portion of the planet's radius rather than being a small, dense nucleus at the center. These findings indicate Jupiter's formation might have been more chaotic and violent than previously thought. Rather than smoothly accumulating material in layers, Jupiter might have experienced massive impacts and mixing events that created its current internal structure. Perhaps the most mind-bending recent discovery. Jupiter might have been even larger in the past. Some calculations suggest early Jupiter could have exceeded twice its current size, with a magnetic field 50 times stronger than today. This massive early Jupiter would have exerted even more dramatic effects on our solar system's formation and evolution. The concept of an even larger ancient Jupiter helps explain puzzling features of our solar system's architecture. It might account for why Mars is so much smaller than Earth, why the asteroid belt never formed into a planet, and why the outer planets possess the characteristics we observe today. As we continue exploring Jupiter's massive scale, we'll delve deeper into how this giant world continues shaping our solar system today. We'll examine incredible atmospheric phenomena playing out across its vast surface, and discover how Jupiter's size compares to the universe's most extreme objects. Jupiter's atmospheric dynamic scale makes Earth's most powerful hurricanes appear like gentle summer breezes. When discussing Jupiter's weather, we're examining storm systems operating on scales our planet-bound minds can barely comprehend. The Great Red Spot, Jupiter's most famous storm, has raged for over 300 years, longer than the United States has existed as a nation. This single storm system currently measures about 10,000 miles wide, meaning you could drop Earth into it and still have thousands of miles of storm remaining. Here's what truly puts Jupiter's atmospheric scale into perspective. The Great Red Spot is actually shrinking. When astronomers began systematic observations in the late 1800s, it exceeded twice its current size, stretching over 25,000 miles across. Even while shrinking, this ancient tempest remains larger than our entire planet. It's not merely a surface phenomenon. Recent Juno spacecraft measurements reveal the Great Red Spot extends over 200 miles deep into Jupiter's atmosphere. For context, if Earth possessed weather systems that deep, they would extend well into what we consider outer space. Jupiter's storm longevity reveals something fundamental about differences between gas giants and terrestrial worlds. On Earth, storms eventually dissipate when encountering land masses, mountains, or other geographical features disrupting their flow patterns. Jupiter lacks solid surface to break up atmospheric circulation. Instead, its storms can persist for decades or centuries, drawing energy from the planet's internal heat and complex interactions between different atmospheric layers. Jupiter generates more heat than it receives from the Sun. This might sound impossible, but it's absolutely true. The planet radiates about 1.6 times more energy into space than it absorbs from solar radiation. This excess heat originates from gravitational compression. Jupiter continues slowly contracting from its formation 4.6 billion years ago. This ongoing contraction generates tremendous thermal energy amounts. It's like a cosmic hand warmer that's been slowly releasing heat for billions of years. This internal heat source drives atmospheric circulation patterns spanning thousands of miles. Jupiter's atmosphere organizes into distinct cloud bands circling the planet parallel to its equator. These bands, called zones and belts, are created by powerful jet streams reaching speeds over 400 mPa. Zones appear bright because they contain ammonia ice crystal clouds high in the atmosphere, while darker belts represent regions where gas sinks deeper into the planet's interior. The colors in Jupiter's atmosphere tell stories of complex chemistry operating on planetary scales. Browns, reds, and yellows originate from organic compounds created when lightning and solar radiation interact with methane, ammonia, and other trace atmospheric gases. These chemical reactions produce molecules called tholins, giving Jupiter its distinctive appearance. This atmospheric chemistry's scale is staggering. Jupiter's atmosphere contains trace water vapor amounts that, when calculated across the planet's enormous volume, likely exceed all water in Earth's oceans. Lightning on Jupiter operates on scales dwarfing terrestrial thunderstorms. Individual lightning bolts can be thousands of times more powerful than Earth's, occurring in regions where atmospheric pressure exceeds Earth's surface pressure many times over. The Juno spacecraft has detected lightning strikes generating radio waves so powerful they can be detected from millions of miles away. These aren't merely weather phenomena, they're electromagnetic events influencing the entire Jovian system. Rapid rotation creating Jupiter's oblate shape also generates some of the solar system's most complex atmospheric dynamics. Different latitudes rotate at different speeds, creating shear zones where adjacent atmospheric bands slide past each other at hundreds of miles per hour. These shear zones become breeding grounds for new storm systems and help maintain the planet's distinctive banded appearance. Jupiter's influence extends far beyond its atmospheric boundaries. The planet's enormous magnetosphere creates radiation environments so intense they fundamentally shape its entire moon system's characteristics. The 4 largest moons, discovered by Galileo over 400 years ago, exist in gravitational and magnetic environments unlike anywhere else in our solar system. Io, the innermost large moon, experiences tidal forces from Jupiter 7,000 times stronger than tidal forces Earth exerts on our moon. These forces constantly flex and stretch Io's interior, generating sufficient heat to power the 400 active volcanoes across its surface. Volcanic plumes from these eruptions can shoot material over 300 miles high, creating thin sulfur dioxide atmospheres that get stripped away by Jupiter's magnetic field, forming donut-shaped charged particle rings around the planet. Europa, Jupiter's second large moon, harbours what might be our solar system's largest ocean beneath its icy surface. This subsurface ocean contains more than twice as much water as all Earth's oceans combined. The ocean exists because Jupiter's tidal forces generate sufficient heat to keep water liquid despite Europa being much farther from the Sun than Earth. This hidden ocean scale is mind-boggling. It's estimated to be 40 to 100 miles deep compared to Earth's oceans, which average less than 2.5 miles in depth. Ganymede, Jupiter's largest moon, exceeds planet Mercury's size and possesses its own magnetic field generated by a liquid iron core. The interaction between Ganymede's magnetic field and Jupiter's creates auroras at Ganymede's poles, observed by the Hubble Space Telescope. These auroras provide evidence for yet another subsurface ocean sandwiched between ice layers within Ganymede's interior. Callisto, the outermost large moon, represents one of our solar system's most heavily cratered objects, bearing scars from billions of years of impacts. Its surface is so ancient and battered it provides windows into our solar system's early history, when planets were still forming and debris was much more common. The Jovian moon system's scale becomes even more impressive considering the smaller moons. Jupiter possesses at least 79 known moons, with more discovered regularly as our telescopes become more sensitive. Many smaller moons are likely captured asteroids snatched from original orbits by Jupiter's immense gravitational pull. Some tiny moons have such eccentric orbits they require years to complete single trips around Jupiter. Gravitational interactions within the Jovian system create complex orbital mechanics dances. The 3 inner moons, Io, Europa, and Ganymede, are locked in what's called Laplace resonance. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2 orbits. and Io completes exactly 4. This precise mathematical relationship helps maintain system orbital stability and contributes to tidal heating, driving geological activity on these moons. Jupiter's role as gravitational shepherd extends throughout our solar system. The Trojan asteroids, 2 rocky body groups sharing Jupiter's solar orbit, provide evidence of the planet's long-term gravitational influence. These asteroids occupy stable gravitational zones called Lagrange points, located 60 degrees ahead of and behind Jupiter in its orbit. Over 7,000 known Trojan asteroids exist, representing material gravitationally captured and held in place by Jupiter for billions of years. Jupiter's gravitational influence reaches even further into the outer solar system. The planet acts like a gravitational gateway, determining which comets from the distant Kuiper belt and Oort cloud make their way into the inner solar system. When these icy bodies venture too close to Jupiter, they can be either ejected from the solar system entirely or redirected into new orbits, bringing them closer to the Sun. Some of the most spectacular comets visible from Earth owe their trajectories to gravitational encounters with Jupiter. Comet Shoemaker-Levy 9 famously collided with Jupiter in 1994, after being torn apart by the planet's tidal forces during a previous close approach. The impact created explosion sites larger than Earth and provided astronomers with dramatic demonstrations of Jupiter's role as cosmic protector, absorbing impacts that might otherwise threaten inner planets. Jupiter's protective influence scale becomes clear when considering statistics. Computer simulations suggest that without Jupiter's gravitational presence, Earth would experience large asteroid and comet impacts at rates hundreds of times higher than we actually observe. These impacts could have prevented complex life development or caused multiple mass extinctions throughout Earth's history. However, Jupiter's gravitational influence isn't always protective. The same gravitational forces that can deflect dangerous objects away from Earth can also redirect them toward us. Some scientists argue Jupiter acts more like a gravitational stirrer than a shield, sometimes increasing impact rates in the inner solar system. Reality probably lies somewhere between, with Jupiter's net effect being protective, but with occasional exceptions. Recent exoplanet discoveries, planets orbiting other stars, have provided new perspectives on how unusual Jupiter's size and position might be. Most giant planets discovered around other stars orbit much closer to their host stars than Jupiter orbits our Sun. These hot Jupiters have orbital periods of days or weeks rather than Jupiter's 12-year orbit. Close-in giant existence suggests planetary migration is common during solar system formation, raising questions about how Jupiter managed to end up in its current distant orbit. Some models suggest Jupiter actually migrated inward toward the Sun during early solar system formation stages before reversing course and moving back outward. This hypothetical journey, called the Grand Tack model, could explain many puzzling features of our solar system's architecture. If Jupiter had continued its inward migration, it might have disrupted terrestrial planet formation entirely. Jupiter's size and mass study continues revealing new insights about planetary formation throughout the universe. The planet serves as a natural laboratory for understanding how gas giants form and evolve. Every new measurement of Jupiter's internal structure, atmospheric composition, or magnetic field provides clues about processes that shaped not only our solar system, but potentially countless others throughout the galaxy. As we push deeper into exploring Jupiter's massive scale, we begin encountering questions challenging our understanding of what it means to be a planet. At what point does a planet become so large it should be classified as something else entirely? How do physical processes operating within Jupiter compare to those in brown dwarfs? Those failed stars bridging gaps between planets and true stars. Jupiter exists at a fascinating boundary in the cosmic object hierarchy. It's too small to be a star, too large to be considered a typical planet, and too massive to ignore when considering our solar system's dynamics. In many ways, Jupiter represents a category unto itself, a gas giant whose influence extends far beyond its physical boundaries and whose story intimately connects to every other object's story in our cosmic neighborhood. The more we learn about Jupiter's true scale and influence, the more we realize that understanding this giant planet is key to understanding our place in the universe. Jupiter didn't simply happen to form in our solar system. It fundamentally shaped the solar system we inhabit today. Jupiter's classification question becomes even more intriguing when we dive into cutting-edge discoveries about its interior structure. Until recently, scientists assumed Jupiter possessed a small, dense core surrounded by metallic hydrogen layers and regular hydrogen atmosphere. But the Juno mission has completely revolutionized our understanding of what lies beneath Jupiter's cloud tops. What Juno found was shocking. Instead of a small, well-defined core, Jupiter appears to have what scientists call a fuzzy, or dilute core, extending through nearly half the planet's radius. This isn't the neat layered structure we expected. It's more like a gradual transition from rock and ice mixed with hydrogen and helium, stretching across tens of thousands of miles. Consider what this means. Jupiter's core region is larger than entire planet Earth, and it's not even a solid boundary. It's a transitional zone where distinctions between core and atmosphere become meaningless. This discovery suggests Jupiter's formation was far more violent and chaotic than we previously imagined. The leading theory now proposes that during Jupiter's early formation, it suffered massive impacts from other planetary embryos, objects potentially as large as Earth itself. These collisions would have stirred up Jupiter's interior, mixing rocky core material with hydrogen and helium atmosphere. The result is the fuzzy core structure we observe today. Here's where Jupiter's story becomes even more mind-bending. Pressures and temperatures inside this giant world reach extremes that don't exist anywhere else in our solar system. About 7,000 miles below cloud tops, pressure becomes so intense that hydrogen transforms into that exotic metallic state. This isn't just a phase change like water turning to ice. This is hydrogen being squeezed so hard that its electrons are stripped away, creating liquid that can conduct electricity like copper wire. The metallic hydrogen region extends for thousands of miles through Jupiter's interior, creating the largest volume of this exotic matter anywhere in the known universe. On Earth, we can only create metallic hydrogen for microseconds in our most powerful laboratory presses. Inside Jupiter, it exists in mind-boggling quantities, forming vast liquid metal oceans under pressures millions of times greater than Earth's atmosphere. This metallic hydrogen ocean drives Jupiter's incredible magnetic field. As the planet rotates every 10 hours, this conducting fluid generates electrical currents, creating magnetic field lines stretching millions of miles into space. The energy contained in Jupiter's magnetic field is so enormous that if we could somehow harvest it, it could power human civilization for billions of years. Jupiter's magnetic environment isn't just powerful, it's also incredibly complex. Unlike Earth's relatively simple dipole magnetic field, Jupiter's field has multiple poles and complicated structures that shift and change over time. Recent observations show Jupiter's magnetic field is actually changing much more rapidly than Earth's, with some regions showing significant variations over just a few years. This changing magnetic field has profound effects on Jupiter's radiation environment. The planet traps charged particles in radiation belts, making the space around Jupiter one of our solar system's most dangerous regions for both spacecraft and any potential future human explorers. Radiation levels near Jupiter are so intense they would deliver lethal doses to unprotected humans in minutes. Jupiter's magnetic influence scale extends far beyond what we can see. Radio telescopes on Earth regularly detect powerful radio emissions from Jupiter, created by charged particles spiraling along magnetic field lines at nearly light speed. These radio signals are so strong that amateur radio operators with basic equipment can detect them from Jupiter's orbit over 400 million miles away. The interaction between Jupiter's magnetic field and solar wind creates bow shock waves in space, beginning millions of miles before solar wind even reaches Jupiter's magnetosphere. It's like Jupiter creates its own weather system in space vacuum, deflecting and reshaping charged particle streams flowing outward from our Sun. When we discuss Jupiter's size, we often focus on physical dimensions, but its magnetic presence makes it effectively much larger than its physical body. The total space volume dominated by Jupiter's magnetic field is comparable to the volume inside Mercury's solar orbit. In a very real sense, Jupiter's influence extends across a space region larger than some planetary orbits. This magnetic dominance has shaped Jupiter's entire moon system evolution. The 4 largest moons all orbit within Jupiter's magnetosphere, subjecting them to constant high-energy particle bombardment. Over billions of years, this radiation has darkened their surfaces and driven chemical changes in their atmospheres and surface materials. The radiation environment around Jupiter creates phenomena existing nowhere else in our solar system. Io's volcanoes don't just spew lava and gas into space. They also inject charged particles directly into Jupiter's magnetic field, creating a torus of glowing plasma orbiting the planet at Io's distance. This plasma torus is invisible to human eyes but glows brightly in ultraviolet and radio wavelengths, creating what's essentially a 3,000-mile wide ring of superheated gas around Jupiter. The electrical connection between Jupiter and Io carries current of about 5 million amperes, equivalent to dozens of nuclear power plants' power output. This current flow creates auroral displays at Jupiter's poles hundreds of times more powerful than Earth's northern and southern lights. These Jovian auroras cover areas larger than Earth and shine with intensities visible from space even during Jupiter's daytime. Recent discoveries reveal Jupiter's auroras are not only incredibly powerful, but also surprisingly variable. Unlike Earth's auroras, primarily driven by solar wind interactions, Jupiter's auroras are largely powered by the planet's own rotation and moon interactions. The result is auroral displays that can persist for hours or days and cover enormous regions of Jupiter's polar atmosphere. The energy scale involved in Jupiter's magnetosphere becomes clear when considering that the planet's magnetic field stores more energy than the total kinetic energy of all asteroid belt asteroids. This energy occasionally gets released in explosive events, sending shock waves throughout the Jovian system and detectable by spacecraft throughout the outer solar system. Jupiter's rapid rotation, completing one full spin every 9 hours, creates additional complications in its magnetic field structure. Centrifugal force from this rapid rotation stretches magnetic field lines outward, creating disk-like structures in the equatorial plane extending far beyond Jupiter's outermost moon orbits. Material trapped in this magnetic disk gets spun up to incredible speeds, creating charged particle populations moving at thousands of miles per second. The combination of Jupiter's size, mass, rotation, and magnetic field creates what scientists call a mini-magnetosphere, operating like a scaled-down version of the entire solar system. Jupiter's moons orbit within this magnetosphere like planets orbiting within stellar wind, experiencing conditions that are simultaneously familiar and utterly alien. Perhaps the most remarkable aspect of Jupiter's scale is how it continues surprising us even after centuries of observation. Every new Jupiter mission reveals phenomena unpredicted by our models. The Galileo mission discovered Jupiter's magnetic field is much more complex than expected. The Juno mission found the planet's interior structure completely differs from our expectations. The James Webb Space Telescope has recently provided new insights into Jupiter's atmospheric dynamics, revealing temperature and chemical variations across the planet's surface invisible to previous instruments. These observations show us Jupiter's atmosphere is even more complex and dynamic than we realized, with temperature differences and chemical gradients operating on scales spanning thousands of miles. One of the most recent discoveries about Jupiter's scale comes from Juno spacecraft studies of its gravitational field. These measurements reveal Jupiter's interior contains regions of different density extending deep into the planet. These density variations suggest Jupiter's formation involved processes we're still trying to understand, possibly including multiple planetary embryo mergers during early solar system formation stages. Gravitational mapping has also revealed Jupiter's core extends much farther from the planet's center than anyone expected. Instead of being a compact ball of rock and ice, Jupiter's core appears to be a partially dissolved mixture of heavy elements and hydrogen extending across nearly 60% of the planet's radius. This means Jupiter's core is larger than entire planet Saturn. These Jupiter internal structure discoveries have implications extending far beyond our solar system. As we discover more exoplanets around other stars, many of which are gas giants similar to Jupiter, understanding how these worlds form and evolve becomes crucial for understanding planetary systems throughout the galaxy. Jupiter serves as our nearest gas giant example, a laboratory where we can study processes that probably occur around countless other stars. The more we learn about Jupiter's true scale and complexity, the more we realize this giant planet represents a fundamental world type that may be among the most common in our galaxy. Recent surveys suggest gas giants like Jupiter may be present in significant fractions of planetary systems, making Jupiter not just a local curiosity, but a representative of a major planetary object class throughout the universe. Jupiter's influence on our solar system continues unfolding in ways we're still discovering. Computer simulations of early solar system evolution suggest Jupiter's gravitational influence may have prevented planet formation between Mars and Jupiter, instead creating the asteroid belt we see today. Without Jupiter's presence, our solar system might have contained an additional terrestrial planet, fundamentally altering our cosmic neighborhood's architecture. The same gravitational influences that prevented asteroid belt planet formation may have also played crucial roles in delivering water to Earth during the early bombardment period. Jupiter's gravity would have scattered comets and asteroids throughout the inner solar system, some of which would have collided with Earth, potentially providing much of the water in our oceans. As we continue studying Jupiter's massive scale and its effects on our solar system, we're beginning to understand that this giant planet isn't just a member of our cosmic family. It's more like the patriarch whose presence has shaped every other world's characteristics and destinies in our solar system. From the asteroid belt to the outer reaches of the Kuiper belt, Jupiter's gravitational influence has left its mark on virtually every object orbiting our Sun. Jupiter's scale study also provides insights into fundamental physics of planetary formation and evolution. The processes that created Jupiter, from initial solid material accumulation to runaway gas accretion from the solar nebula, represent some of the most dramatic events in our solar system's history. Understanding these processes helps us comprehend how planetary systems form and evolve around other stars throughout the galaxy. Jupiter's influence on planetary formation extends even deeper when we consider its growth timing. Recent computer models suggest Jupiter reached its current size remarkably quickly in cosmic terms, achieving most of its mass within just the first few million years of our solar system's existence. This rapid formation had cascading effects throughout the entire solar neighborhood. During this early period, Jupiter acted like a cosmic bulldozer, clearing out vast regions of the primordial solar disk. The planet's gravity carved gaps in the gas and dust disk surrounding the young Sun, creating zones where smaller objects couldn't accumulate into larger bodies. This gravitational clearing process explains why the outer solar system beyond Jupiter contains relatively few large objects compared to expectations. Jupiter's early dominance created another fascinating phenomenon. As it grew, Jupiter began migrating inward toward the Sun, drawn by gravitational interactions with remaining disk material. This inward migration could have been catastrophic for the inner solar system. If Jupiter had continued moving sunward, it might have scattered or destroyed rocky material that eventually formed Mercury, Venus, Earth, and Mars. Fortunately for us, something stopped Jupiter's inward journey. The most likely explanation involves Saturn, our solar system's second largest planet. As Saturn grew and began its own migration, gravitational interaction between the two gas giants created resonance that reversed their motion, sending both planets back outward to roughly their current positions. This gravitational dance between Jupiter and Saturn, known as the Grand Tack model, may have been the crucial event allowing terrestrial planets like Earth to form at all. This early migration scale becomes mind-boggling when considering distances involved. Jupiter may have travelled inward to within Mars's orbit before reversing course and moving back out to its current position beyond the asteroid belt. That's a round trip of hundreds of millions of miles, accomplished by an object with more mass than 2.5 Earths combined. Imagine the gravitational chaos this journey must have created throughout the early solar system. This migration scenario helps explain one of our solar system's most puzzling features: why Mars is so much smaller than Earth. Computer simulations suggest Jupiter's inward journey truncated Mars's formation, preventing it from accreting additional material that would have made it a much larger world. Without Jupiter's gravitational interference, Mars might have grown to be similar to Earth in size, or even larger. Jupiter's early migration implications extend to life's very existence on Earth. If Jupiter had followed a different path, or if its interaction with Saturn had played out differently, Earth might never have formed in the habitable zone around our Sun. The delicate balance allowing our planet to develop liquid water oceans and stable climate may depend entirely on the specific gravitational choreography that occurred between Jupiter and Saturn over 4 billion years ago. One of the most remarkable examples of Jupiter's long-term influence involves asteroid and comet orbital characteristics. Jupiter's gravity creates what scientists call resonances, specific orbital periods where small objects experience regular gravitational tugs that can either stabilize their orbits or eject them from the solar system entirely. These resonances create complex gravitational influence webs extending throughout the asteroid belt and beyond. The Kirkwood gaps in the asteroid belt provide visible evidence of these resonances. These are regions where asteroids are notably sparse, cleared out over millions of years by Jupiter's repeating gravitational influence. An asteroid in one of these gaps experiences gravitational tugs from Jupiter at the same point in its orbit repeatedly, gradually increasing the asteroid's orbital eccentricity until it either collides with another object or gets ejected from the belt entirely. Jupiter's gravitational reach scale becomes evident when considering these clearing effects operate over distances of hundreds of millions of miles. Jupiter doesn't need proximity to an object to influence its fate. The planet's massive gravity can gradually reshape orbits through accumulated effects, playing out over millions of orbital periods. This long-term gravitational sculpting has profound implications for understanding Earth's impact hazards. Jupiter acts as both shield and source of potentially dangerous objects. While the planet's gravity deflects many comets and asteroids away from the inner solar system, it also occasionally redirects objects onto Earth-crossing orbits. The net effect appears protective, but the relationship is complex and continues being studied by planetary scientists. Jupiter's gravitational influence also extends to our solar system's very edge. The planet helps determine which objects from the distant Oort cloud, a spherical shell of comets surrounding our solar system, eventually make their way inward to become visible comets. When these distant icy bodies are nudged by passing stars or galactic tides, their subsequent paths through the solar system are largely determined by gravitational encounters with Jupiter. Some of Earth's most spectacular visible comets owe their current orbits to past Jupiter encounters. The planet can capture comets into shorter period orbits, creating the Jupiter family comet group that returns to the inner solar system every few years or decades. Alternatively, Jupiter can accelerate comets to such high velocities they're ejected from the solar system entirely, never to return. This gravitational influence scale becomes clear when considering Jupiter has been performing cosmic traffic control for over 4 billion years. Countless gravitational encounters' cumulative effect has fundamentally shaped small body populations throughout our solar system. Without Jupiter's presence, asteroid, comet, and other debris distribution would be completely different. Recent Jupiter-Moon discoveries have revealed another dimension of the planet's massive scale. The Jovian system contains at least 79 known moons, ranging from 4 giant Galilean satellites to tiny captured asteroids just a few miles across. This diverse world collection represents a miniature solar system in its own right, with Jupiter playing central star roles. Gravitational relationships within the Jovian system operate on scales dwarfing anything in the Earth-Moon system. Io, the innermost large moon, experiences tidal forces from Jupiter thousands of times, stronger than tidal forces Earth exerts on our moon. These forces generate so much heat within Io that the moon has become our solar system's most volcanically active world, with over 400 active volcanoes dotting its surface. Io's volcanic activity operates on scales challenging our understanding of planetary geology. Some volcanic plumes shoot material over 300 miles high, reaching altitudes where spacecraft orbit around Earth. Total heat output from Io's volcanic activity exceeds all terrestrial volcano heat output combined by factors of 10 or more. This isn't just geological activity, it's geological hyperactivity driven by Jupiter's immense gravitational field. Europa, Jupiter's second large moon, harbours what may be our solar system's most significant ocean. Beneath its icy surface lies a global ocean containing more than twice as much water as all Earth's oceans combined. This hidden sea exists because Jupiter's tidal forces generate sufficient heat to keep water liquid, despite Europa being much farther from the Sun than Earth. Europa's subsurface ocean scale is staggering. Recent estimates suggest it may be 40 to 100 miles deep compared to Earth's oceans, which average less than 2.5 miles in depth. This alien ocean's total volume dwarfs all terrestrial water bodies, making Europa potentially our solar system's most water-rich world. Europa's ocean isn't just large, it's also potentially habitable. The interaction between the ocean and Europa's rocky interior may create hydrothermal vents similar to those found on Earth's ocean floors. These environments could provide energy and chemical ingredients necessary for life to develop and thrive. The possibility that Jupiter's tidal heating could power an entire biosphere beneath Europa's ice represents one of astrobiology's most exciting prospects. Ganymede, Jupiter's largest moon, is itself larger than planet Mercury, and possesses its own magnetic field generated by a liquid iron core. The interaction between Ganymede's magnetic field and Jupiter's creates complex electromagnetic phenomena observable from Earth. Recent observations have detected auroras at Ganymede's poles created by charged particles from Jupiter's magnetosphere interacting with Ganymede's thin atmosphere. The magnetic interaction between Jupiter and Ganymede also provides evidence for yet another subsurface ocean within Ganymede's interior. The way Ganymede's magnetic field responds to Jupiter's changing magnetic environment indicates a conducting layer presence, most likely a salty ocean sandwiched between ice layers deep within the Moon's interior. Callisto, the outermost large moon, presents a different face of the Jovian system. Its heavily cratered surface records billions of years of impacts, providing windows into our solar system's early history, when asteroid and comet bombardment was much more intense. These ancient scar preservation tells us Callisto has remained geologically inactive throughout most of its history. Unlike its inner companions that have been reshaped by Jupiter's tidal forces, Callisto has preserved surface features from our solar system's earliest epochs. The diversity within Jupiter's moon system demonstrates how the planet's gravitational influence creates different environments at different distances. Close to Jupiter, tidal forces dominate, creating geologically active worlds like Io and Europa. Farther out, these forces weaken, allowing moons like Callisto to preserve ancient surface features. This gravitational influence gradient creates natural laboratories for studying how tidal forces affect planetary evolution. Beyond the 4 large Galilean satellites, Jupiter's gravitational reach extends to capture dozens of smaller moons. Many of these are likely asteroids that wandered too close to Jupiter and became permanently trapped in its gravitational field. Some captured moons have highly elliptical orbits taking them millions of miles from Jupiter before swinging back in close approaches. Jupiter's gravitational capture zone scale is enormous. Objects can be captured into Jupiter orbit from distances comparable to Earth-Moon separation. This capture process continues today as Jupiter occasionally snares passing asteroids or comets, adding new members to its already extensive satellite family. Jupiter's moon system study has also revealed complex orbital dynamics operating within the planet's gravitational field. The 3 innermost large moons are locked in precise gravitational resonance, with Io completing 4 orbits for every 2 Europa orbits and every 1 Ganymede orbit. This mathematical precision isn't coincidental, but represents stable configuration that has persisted for billions of years. These orbital resonances demonstrate how Jupiter's gravity creates order within apparent chaos. While gravitational interactions within the Jovian system are incredibly complex, involving dozens of moons and countless smaller objects, they settle into stable patterns persisting for geological ages. The same gravitational forces creating tidal heating and geological activity also maintain precise orbital relationships keeping the system stable. Recent Jupiter missions have revealed the planet's influence on its moons extends beyond simple gravitational and tidal effects. Jupiter's powerful magnetosphere creates radiation environments continuously bombarding inner moon surfaces, driving chemical changes and creating exotic compounds that don't exist naturally on Earth. Over billions of years, this radiation processing has fundamentally altered surface compositions of moons like Europa and Ganymede. The interaction between Jupiter's magnetosphere and its moons also creates electrical currents flowing through space vacuum. The current flowing between Jupiter and Io carries millions of amperes, more electrical power than many terrestrial power grids. This current flow heats Jupiter's upper atmosphere and contributes to the planet's powerful auroral displays. Jupiter's auroras operate on scales dwarfing their terrestrial counterparts. Individual auroral features can be larger than Earth and persist for days or weeks. Jupiter's total auroral power output exceeds all human civilization power output by factors of thousands or millions. These aren't just pretty skylights. They're manifestations of electromagnetic processes operating on planetary scales. The electromagnetic phenomena scale around Jupiter extends far beyond the planet's physical boundaries. Jupiter's radio emissions can be detected by amateur radio operators on Earth using relatively simple equipment. These radio signals are generated by electrons spiraling along Jupiter's magnetic field lines at nearly light speed, creating natural radio transmitters more powerful than any human-built devices. Jupiter's radio emissions vary in complex patterns, reflecting dynamic interactions between the planet's magnetosphere and its moons. When Io passes through certain Jupiter magnetic field regions, radio output increases dramatically, creating what scientists call Io-controlled emissions. These radio storms can be detected from Earth despite enormous distances, demonstrating incredible electromagnetic process scales operating within the Jovian system. Jupiter's electromagnetic environment study has provided insights into similar processes that may occur around other giant planets throughout the galaxy. As we discover more exoplanets, particularly gas giants similar to Jupiter, understanding electromagnetic phenomena around our own giant planet becomes crucial for interpreting distant world observations. Jupiter's massive scale continues influencing our understanding of planetary formation and evolution throughout the universe. The planet serves as a gas giant prototype, providing detailed information about processes probably occurring around countless other stars. Every new discovery about Jupiter's structure, composition, or behavior adds to our understanding of how planetary systems form and evolve. The recent discovery that Jupiter's core is much larger and more diffuse than expected has implications for giant planet formation models throughout the galaxy. If Jupiter's formation involved violent impacts and mixing processes, similar events probably occurred during gas giant formation around other stars. This means exoplanet internal structures may be much more complex and varied than we previously assumed. Jupiter's ongoing massive-scale study also provides insights into planetary interior fundamental physics. Extreme pressures and temperatures within Jupiter, create conditions that can't be replicated in terrestrial laboratories. By studying Jupiter's structure and behavior, scientists can test theories about matter behavior under extreme conditions, advancing our physics understanding itself. As our exploration tools become more sophisticated, we continue discovering new aspects of Jupiter's enormous scale and influence. Future Jupiter missions will undoubtedly reveal even more surprises about this giant world, adding new chapters to the story of how massive objects shape cosmic environments around them. The question of how massive Jupiter truly is extends far beyond simple size and weight measurements. Jupiter's mass creates gravitational fields, electromagnetic phenomena, and dynamic processes operating on scales spanning millions of miles and billions of years. The planet's influence permeates every aspect of our solar system structure and evolution, making Jupiter not just the largest planet, but also our cosmic family's most influential member. Understanding Jupiter's true scale requires us to step back and consider time itself. This massive world has been performing its gravitational symphony for over 4 billion years. Its influence's cumulative effects have shaped every corner of our solar system in ways continuing to unfold today. When we discuss Jupiter's mass affecting other objects, we're not just talking about immediate gravitational pulls. We're discussing processes operating across geological timescales, where tiny gravitational nudges accumulate over millions of orbital periods to create dramatic changes in our solar system's architecture. Consider the asteroid belt, that rocky debris collection orbiting between Mars and Jupiter. At first glance, it might seem like random scattering of leftover material from our solar system's formation. Look more closely, and you'll see Jupiter's gravity's invisible hand written across its structure. The belt contains distinct gaps called Kirkwood gaps, where asteroids are notably absent. These aren't random empty spaces. They're results of Jupiter's gravitational resonances clearing out specific orbital zones over millions of years. An asteroid unfortunate enough to orbit in one of these resonance zones experiences gravitational tugs from Jupiter at exactly the same orbital point repeatedly for millions of years. Each tug is tiny, almost imperceptible. Over time, these accumulated nudges increase the asteroid's orbital eccentricity until its path becomes so elongated it either collides with another object or gets ejected from the belt entirely. This gravitational sculpting scale becomes apparent when realizing Jupiter is performing orbital engineering across distances of hundreds of millions of miles. The planet doesn't need proximity to these asteroids to control their fate. Its massive gravity reaches across void, subtly but inexorably reshaping matter distribution throughout the solar system. This same gravitational influence extends much farther out, affecting objects in our solar system's distant reaches. The Kuiper Belt, that region beyond Neptune where Pluto and thousands of other icy bodies orbit, bears Jupiter's gravitational influence signature. Even at distances of 3 to 5 billion miles from Jupiter, Kuiper Belt objects move in patterns reflecting the giant planet's presence. Some of the most dramatic examples of Jupiter's long-range gravitational influence come from studying comets. These icy visitors from the outer solar system often owe their spectacular appearances to gravitational encounters with Jupiter that occurred decades or centuries earlier. Jupiter can capture comets from highly elongated orbits and shepherd them into shorter period orbits, bringing them back to the inner solar system every few years. These gravitational manipulation scales are staggering. Jupiter can take comets that originally took thousands of years to complete one orbit and transform them into regular visitors with orbital periods of just 5 or 6 years. Alternatively, Jupiter can accelerate comets to such high velocities they're ejected from the solar system entirely, sent on one-way journeys to interstellar space. Famous comet Shoemaker-Levy 9 provided dramatic demonstration of Jupiter's gravitational power in 1994. This comet had been captured by Jupiter's gravity during a previous close encounter, and tidal forces from the giant planet tore it apart into fragment strings. When these fragments eventually collided with Jupiter, they created impact sites larger than Earth and explosions visible from telescopes around our planet. Jupiter's gravitational influence operates on scales even larger than individual comet encounters. The planet acts as a kind of gravitational traffic controller for the entire outer solar system, determining which objects from the distant Oort cloud eventually make their way inward to become visible comets. When these distant icy bodies are nudged by passing stars or galactic tides, their subsequent journeys through the solar system are largely controlled by Jupiter's massive gravity. The Oort cloud itself, that spherical comet shell surrounding our solar system at distances of thousands of astronomical units, exists in its current form partly because of Jupiter's gravitational influence during early solar system formation stages. As Jupiter grew to its current size, its gravity helped scatter countless icy planetesimals outward, populating our solar system's distant reaches with the comet reservoir that occasionally visits the inner solar system today. This scattering process operated on truly cosmic scales. Objects that formed relatively close to the Sun, perhaps in the region where giant planets now orbit, were flung outward by Jupiter's gravity to distances thousands of times farther from the Sun. Some scattered objects may have been ejected from the solar system entirely, contributing to rogue planet populations drifting through interstellar space. Jupiter's influence scale becomes even more impressive when considering its role in delivering water to the inner solar system. During the early bombardment period roughly 4 billion years ago, Jupiter's gravity scattered water-rich asteroids and comets throughout the solar system. Some of these objects collided with Earth, potentially providing much of the water filling our oceans today. Recent computer simulations suggest that without Jupiter's gravitational stirring, Earth might have remained a dry, lifeless world. The giant planet's influence was crucial in delivering raw materials necessary for life to develop on our planet. In a very real sense, every drop of water in Earth's oceans may be there because of gravitational interactions with Jupiter that occurred billions of years ago. Jupiter's role in shaping our solar system extends beyond just moving objects around. The planet's massive gravity has also influenced the very structure of space itself in our cosmic neighborhood. Einstein's general relativity theory tells us that mass curves spacetime, and Jupiter's enormous mass creates significant gravitational wells, affecting trajectories of everything passing nearby. This spacetime curvature around Jupiter is so pronounced, it affects spacecraft paths visiting the outer solar system. Mission planners routinely use Jupiter's gravity to accelerate and redirect spacecraft, a technique called gravitational slingshot or gravity assist. By carefully timing spacecraft approaches to Jupiter, engineers can increase velocity and change direction without using additional fuel. The Voyager missions provide perhaps the most famous example of using Jupiter's gravity for space exploration. Both Voyager 1 and Voyager 2 used Jupiter's immense gravitational field to accelerate toward outer planets, achieving velocities impossible with chemical rockets alone. Jupiter's gravitational boost allowed these spacecraft to visit Saturn, Uranus, and Neptune, eventually becoming the first human-made objects to enter interstellar space. The precision required for these gravitational assists demonstrates Jupiter's massive gravitational field's predictable nature. Engineers can calculate exactly how Jupiter's gravity will affect spacecraft trajectories years in advance, planning complex multi-planet missions relying on precise timing and positioning. The fact that these calculations work so perfectly testifies to our understanding of how Jupiter's mass curves spacetime. Jupiter's gravitational influence isn't limited to objects passing through the solar system. The planet's massive presence actually affects our Sun, causing our star to wobble slightly as Jupiter orbits around it. This wobble is tiny from our perspective, but it's measurable and detectable from Earth. The Sun-Jupiter system actually orbits around their common mass center called the barycenter. Because Jupiter is so much less massive than the Sun, this barycenter lies just outside the Sun's surface. As Jupiter completes its 12-year orbit, it pulls the Sun around this barycenter, creating regular wobbling motion detectable by sensitive instruments. This solar wobble caused by Jupiter has become one of the primary techniques for discovering planets around other stars. When astronomers observe distant stars wobbling in regular patterns, they know there's likely a massive planet, probably similar to Jupiter, orbiting that star. Hundreds of exoplanets have been discovered using this technique, many of them gas giants comparable in mass to Jupiter. Detection of these Jupiter-like exoplanets has revealed something surprising about our solar system. Most gas giants discovered around other stars orbit much closer to their host stars than Jupiter orbits our Sun. These hot Jupiters complete orbits in days or weeks rather than Jupiter's 12-year period. This suggests our solar system may be somewhat unusual in having its giant planet in a distant orbit. Hot Jupiter prevalence around other stars has led to new theories about planetary migration during solar system formation. It appears gas giants commonly migrate inward toward their host stars after forming in planetary system outer regions. Jupiter's location in our solar system suggests something stopped its inward migration, allowing it to remain in its current distant orbit. The most likely explanation involves Saturn, our solar system's second largest planet. Computer simulations suggest that as both Jupiter and Saturn grew and began migrating inward, their gravitational interaction created resonance that reversed their motion, sending both planets back outward to roughly their current positions. This gravitational dance between the two gas giants may have been the crucial event preventing Jupiter from becoming a hot Jupiter and destroying the inner solar system. This early planetary migration scale is difficult to comprehend. Jupiter, with mass greater than all other planets combined, may have travelled hundreds of millions of miles inward toward the Sun before reversing course and moving back out to its current position. The gravitational chaos this journey must have created throughout the early solar system would have affected every object in the solar nebula. This migration scenario helps explain many puzzling features of our solar system's architecture. Mars's small size compared to Earth and Venus may result from Jupiter's inward journey, truncating the planet's formation. The asteroid belt's current structure may reflect gravitational stirring that occurred as Jupiter passed through the region. Even Earth's orbital characteristics may have been influenced by Jupiter's early migration. Jupiter's formation and migration timing may have been crucial for life's development on Earth. If Jupiter had formed earlier or later, or if its interaction with Saturn had played out differently, the inner solar system might look completely different today. Earth might never have formed in the habitable zone, or it might have been scattered into different orbit where liquid water couldn't exist. These possibilities highlight how Jupiter's massive scale has influenced not just our solar system's physical structure, but also conditions that allowed life to develop on Earth. The giant planet's gravitational influence has been shaping our cosmic environment for over 4 billion years, creating the stable, protective solar system architecture that makes Earth's biosphere possible. Recent exoplanetary system discoveries have given us new perspectives on Jupiter's role in our solar system. Many planetary systems discovered around other stars look very different from our own, with giant planets in close orbits and smaller planets scattered throughout their systems. The apparent rarity of solar systems with Jupiter-like planets in Jupiter-like orbits suggests our cosmic neighborhood may be more special than we previously realized. These exoplanetary system studies have also revealed that gas giant formation like Jupiter may be more complex and varied than we once thought. Different stellar environments, different amounts of available material, and different formation event timing can lead to gas giants with very different characteristics and orbital properties. Jupiter's role as a template for understanding gas giants throughout the galaxy makes every new discovery about our local giant planet significant for astronomy as a whole. The internal structure revealed by the Juno mission, complex atmospheric dynamics observed by ground-based telescopes, and electromagnetic phenomena detected by spacecraft all provide insights into processes probably occurring around gas giants throughout the universe. Jupiter's influence scale on our understanding of planetary science extends far beyond our solar system. As we prepare for future missions searching for life around other stars, Jupiter serves as a crucial example of how gas giants can both protect and threaten life development on smaller rocky planets. Understanding Jupiter's role in our solar system helps us predict where we might find habitable worlds around other stars. The implications of Jupiter's massive scale extend far beyond our local cosmic neighborhood, providing crucial insights into the fundamental processes that govern planetary system architecture throughout the galaxy. Recent advances in exoplanet detection have revealed a universe teeming with planetary systems, many of which look nothing like our own. Some systems contain super-Earths, rocky planets larger than Earth but smaller than Neptune, orbiting closer to their stars than Mercury orbits our Sun. Others host multiple gas giants in tight resonant configurations that would be unstable in our solar system. Yet among this bewildering diversity of planetary arrangements, systems with Jupiter-like giants in Jupiter-like orbits appear to be relatively rare. This rarity suggests that our solar system's architecture may be more special than we previously realized, and Jupiter's specific mass, composition, and orbital characteristics may have been crucial factors in creating the stable, life-friendly environment we enjoy today. The study of exoplanetary systems has also revealed that planetary migration, the process by which planets change their orbital distances over time, is far more common than we once thought. Most of the gas giants discovered around other stars show signs of having migrated from their original formation locations, often ending up much closer to their host stars than their initial positions. Jupiter's current location in our solar system suggests that while it may have undergone some migration during its early formation, it ultimately settled into a stable orbit that allowed the inner solar system to develop its current configuration. This delicate balance between migration and stability may be one of the key factors that distinguishes our solar system from the many others we've discovered. Perhaps the most profound aspect of Jupiter's massive scale is how it demonstrates everything's interconnectedness in our solar system. The giant planet operates as a central hub in a vast network of gravitational relationships that extends from the innermost regions of the solar system to the farthest reaches of the Oort cloud. This gravitational web operates on multiple timescales simultaneously. On short timescales, measured in hours, days, or years, Jupiter's gravity creates tidal forces that heat its moons, generates powerful radio emissions, and influences the orbits of passing spacecraft. On intermediate timescales, measured in thousands or millions of years, the planet shepherds asteroid families, captures comets into predictable orbits, and maintains the intricate resonance relationships that keep the outer solar system stable. On the longest timescales, measured in hundreds of millions or billions of years, Jupiter's gravitational influence has sculpted the fundamental architecture of our solar system, determining where planets could form, how much material they could accumulate, and whether they could maintain stable orbits over geological time. This giant planet doesn't exist in isolation. Its gravity reaches across billions of miles to influence objects throughout our cosmic neighborhood, creating a sphere of influence that dwarfs its physical dimensions. Its magnetic field extends far beyond its physical boundaries to interact with solar wind and create phenomena visible from Earth, demonstrating how electromagnetic forces can operate across vast distances in the vacuum of space. Its atmospheric dynamics generate radio emissions detectable by amateur astronomers with backyard equipment, providing a tangible connection between Earth-based observers and the exotic physics operating within Jupiter's magnetosphere. The planet's complex weather systems create atmospheric patterns that persist for centuries, demonstrating how fluid dynamics can organize into stable structures on scales that dwarf anything we see on Earth. Jupiter's story is really our entire solar system's story, but it's also much more than that. The giant planet serves as a Rosetta Stone for understanding gas giant formation and evolution throughout the universe. Every measurement we make of Jupiter's internal structure, every observation of its atmospheric dynamics, and every discovery about its moon system provides insights that extend far beyond our local cosmic neighborhood. The planet's formation history, from its initial accretion as a rocky core to its rapid growth through runaway gas capture, represents a fundamental pathway for gas giant formation that probably occurs around countless other stars. Understanding how this process played out in our solar system helps us interpret observations of young planetary systems where similar events may be occurring today. Jupiter's internal structure, with its exotic metallic hydrogen ocean and diffuse core, provides crucial data for testing theoretical models of planetary interiors under extreme conditions. These models are essential for understanding not just gas giants in our solar system, but also the super-Earths and mini-Neptunes that appear to be among the most common types of planets in the galaxy. The planet's powerful magnetosphere and complex electromagnetic phenomena offer insights into how magnetic fields operate around rapidly rotating massive objects. Similar processes probably occur around gas giant exoplanets, creating radio emissions and auroral displays that may someday be detectable by next-generation telescopes. The giant planet's formation, evolution, and ongoing influence have shaped every aspect of our cosmic environment in ways that continue to surprise researchers. From water in Earth's oceans to asteroid belt structure, from comet orbits to outer planet characteristics, Jupiter's massive presence has left its mark on virtually everything in our solar neighborhood. Consider the intricate dance of materials that led to the formation of the terrestrial planets. During the early stages of solar system formation, when the Sun was still surrounded by a disk of gas and dust, temperature gradients within this disk determined which materials could condense at different distances from the young star. Close to the Sun, where temperatures were highest, only refractory materials like metals and silicates could remain solid. Farther out, where temperatures were lower, water ice and other volatile compounds could condense. Jupiter formed just beyond what astronomers call the snow line, the distance from the Sun where water ice could first condense from the solar nebula. This location was crucial for Jupiter's development because it provided access to both rocky materials from the inner solar system and icy materials from the outer regions. The planet's core could grow rapidly by accreting both types of material, allowing it to reach the critical mass needed to capture gas from the surrounding nebula. But Jupiter's formation had profound consequences for the rest of the solar system. As the giant planet grew, its gravity began to influence the distribution of material throughout the solar disk. Particles that might otherwise have spiraled inward toward the Sun were instead captured by Jupiter's growing gravitational field or scattered to different orbits. This gravitational stirring helped deliver water-rich materials from the outer solar system to the inner regions, where they could eventually be incorporated into the forming terrestrial planets. Without this process, Earth might have formed as a dry desert world, lacking the water necessary for life to develop. As we continue exploring Jupiter with increasingly sophisticated instruments and techniques, we're not just learning about one planet, we're uncovering fundamental processes governing planetary formation and evolution throughout the universe, gaining insights that transform our understanding of how planetary systems develop and maintain their stability over cosmic time. The technological advances that enable modern Jupiter exploration represent marvels of engineering and scientific ingenuity. The Juno spacecraft, currently orbiting Jupiter, carries instruments capable of peering deep into the planet's interior using techniques that were unimaginable just a few decades ago. Microwave radiometers map temperature variations in Jupiter's atmosphere, revealing circulation patterns that extend hundreds of miles below the visible cloud tops. Gravitational sensors measure tiny variations in Jupiter's gravitational field as the spacecraft orbits, providing unprecedented insights into the planet's internal mass distribution. These measurements have revealed that Jupiter's core is much larger and more complex than anyone expected, extending through nearly half the planet's radius and challenging our fundamental understanding of gas giant formation. Magnetometers map the three-dimensional structure of Jupiter's magnetic field with extraordinary precision, revealing complex magnetic structures that vary on timescales ranging from seconds to years. These observations are helping scientists understand how the metallic hydrogen ocean deep within Jupiter generates and maintains the planet's powerful magnetic field. Particle detectors measure the energy and composition of charged particles trapped in Jupiter's radiation belts, providing insights into one of the most extreme radiation environments in the solar system. This data is crucial for understanding how electromagnetic processes operate in the magnetospheres of gas giants, both in our solar system and around other stars. Infrared spectrometers analyze the chemical composition of Jupiter's atmosphere in unprecedented detail, revealing trace gases and complex organic molecules that provide clues about the planet's formation and evolution. These observations are helping scientists understand how atmospheric chemistry operates under the extreme conditions found in gas giant atmospheres. Radio and plasma wave instruments detect electromagnetic phenomena throughout the Jovian system, from low-frequency radio emissions generated by interactions between Jupiter's magnetic field and its moons to high-frequency waves created by lightning in the planet's atmosphere. These measurements provide insights into electromagnetic processes that operate across vast ranges of energy and spatial scales. Future missions to Jupiter will push these capabilities even further. Proposed spacecraft will carry advanced instruments designed to study Jupiter's interior structure in even greater detail, map its gravitational field with unprecedented precision, and explore the complex interactions between the planet and its extensive moon system. Some mission concepts envision atmospheric probes that would descend deep into Jupiter's atmosphere, directly measuring conditions in regions that have never been explored. These probes would face extreme challenges, including crushing pressures, intense radiation, and temperatures hot enough to melt most materials, but they could provide invaluable data about the planet's composition and internal structure. Other proposed missions focus on Jupiter's moons, particularly Europa, Ganymede, and Callisto, which harbour subsurface oceans that may be among the most promising places to search for life beyond Earth. These missions would study the complex interactions between Jupiter's powerful magnetic field and its moon system, investigating how electromagnetic and gravitational forces create and maintain potentially habitable environments. Jupiter's massive scale provides windows into cosmic forces shaping planetary systems everywhere, making this giant world one of the most important objects in our quest to understand our place in the cosmos. The planet serves as a natural laboratory where we can study physical processes that operate under conditions impossible to replicate on Earth or in terrestrial laboratories. The extreme pressures within Jupiter's interior create states of matter that exist nowhere else in the solar system. Metallic hydrogen, which forms the largest ocean in our cosmic neighborhood, exhibits properties that are still not fully understood despite decades of theoretical study. Understanding how this exotic material behaves could provide insights into fundamental physics, from the behavior of materials under extreme conditions to the operation of magnetic dynamos in rapidly rotating bodies. Jupiter's true scale question ultimately leads us to deeper appreciation of the delicate balance allowing our solar system to exist as it does today. This massive world, with its complex internal structure, powerful magnetic field, and extensive moon family, represents one of nature's most impressive achievements, a testament to the remarkable complexity that can emerge from the interplay of fundamental physical forces. The planet's very existence challenges our understanding of the boundaries between different types of celestial objects. Is Jupiter a large planet or a failed star? The question isn't merely academic. It reflects fundamental uncertainties about how we classify objects in the universe, and where we draw the lines between different categories of cosmic phenomena. Jupiter contains the same basic materials as the Sun, hydrogen and helium, but in different proportions and under different conditions. If the planet had been about 80 times more massive, nuclear fusion would have ignited in its core, transforming it from a planet into a star. Our solar system would then be a binary star system, with two sources of light and heat profoundly altering the conditions that allowed life to develop on Earth. This proximity to the stellar threshold raises fascinating questions about the nature of planetary formation and the factors that determine whether a growing protoplanet becomes a gas giant or a brown dwarf. The boundary between these categories is not sharp, but rather represents a continuum of masses and properties, with Jupiter occupying a crucial position near the low-mass end of this spectrum. Yet it also reminds us how much we still need to learn about cosmic processes that created our solar system and continue shaping its evolution. Every new mission to Jupiter reveals surprises that force us to revise our theoretical models and expand our understanding of how massive objects behave under extreme conditions. The recent discovery that Jupiter's core is much larger and more diffuse than expected has implications that extend far beyond our local gas giant. If Jupiter's formation involved violent collisions and mixing processes that created its current internal structure, similar events probably occurred during the formation of gas giants around other stars throughout the galaxy. This means that the internal structures of exoplanets may be far more complex and varied than we previously assumed. Gas giants that appear similar when viewed from distant solar systems may actually have very different internal configurations, depending on the specific circumstances of their formation and early evolution. Every new measurement of Jupiter's gravitational field adds to our understanding of how matter behaves under the extreme conditions found in planetary interiors. The planet's gravitational field reflects the distribution of mass throughout its interior, providing a way to probe regions that will never be directly accessible to spacecraft or instruments. The precision required for these measurements is staggering. The Juno spacecraft must measure variations in Jupiter's gravitational field that are thousands of times smaller than the variations caused by Earth's surface features. Achieving this precision requires sophisticated instruments, precise navigation, and careful analysis of data that pushes the boundaries of current technology. Every fresh observation of its atmospheric dynamics reveals new aspects of how fluid systems behave on planetary scales. Jupiter's atmosphere operates as a vast, complex machine driven by internal heat sources, solar radiation, and the planet's rapid rotation. Understanding how these factors combine to create and maintain the planet's distinctive banded structure and long-lived storm systems provides insights into atmospheric dynamics that apply to gas giants throughout the universe. The longevity of Jupiter's atmospheric features is particularly remarkable. The Great Red Spot has persisted for centuries, maintaining its structure and intensity despite the turbulent environment in which it exists. Understanding how such features can remain stable over such long periods provides insights into the fundamental principles governing fluid dynamics in rotating systems. Every discovery about its internal structure adds another piece to the puzzle of how massive objects influence their cosmic environments. The relationship between Jupiter's internal structure and its magnetic field, for example, provides crucial data for understanding how magnetic dynamos operate in rapidly rotating bodies with complex internal compositions. Jupiter's scale encompasses not just physical dimensions, but also gravitational reach, electromagnetic influence, and evolutionary impact extending across billions of years and billions of miles. The planet's influence operates on scales ranging from the quantum mechanical processes that govern the behavior of materials in its core to the galactic scale forces that occasionally perturb objects in the distant Oort cloud. This multi-scale influence reflects the hierarchical nature of cosmic structure, where phenomena at different scales are interconnected in complex ways. Understanding Jupiter's role in this hierarchy provides insights into how structure and organization emerge in the universe, from the formation of planetary systems to the evolution of galaxies. In contemplating Jupiter's massive scale, we're really contemplating the fundamental question of how matter organizes itself in the universe. The processes that created Jupiter, from the initial condensation of dust grains in the primordial solar nebula to the planet's current status as a complex dynamic system, represent a remarkable example of how simple physical laws can give rise to extraordinary complexity. The formation of Jupiter required the coordination of processes operating across vast ranges of scale and time. Microscopic dust grains had to stick together to form larger particles, which then accumulated into planetesimals, which eventually grew large enough to gravitationally capture gas from the surrounding nebula. Each step in this process operated according to well-understood physical principles, yet the overall result, a giant planet with a complex internal structure and powerful magnetic field, represents an achievement that still challenges our understanding. The planet's current structure reflects billions of years of evolution, driven by the inexorable forces of gravity, thermodynamics, and electromagnetism. The ongoing convection in Jupiter's interior, the circulation patterns in its atmosphere, and the electromagnetic processes in its magnetosphere all represent examples of how energy and matter organize themselves into complex dynamic patterns under the influence of fundamental physical forces, from quantum interactions governing atomic behavior to gravitational forces shaping galactic structure. Jupiter represents a remarkable example of how mass and energy can combine to create complex dynamic systems influencing everything around them. The planet occupies a unique position in the cosmic hierarchy, large enough to exhibit phenomena that don't occur on smaller worlds, yet small enough that we can study it in detail with current technology. The quantum mechanical processes that govern the behavior of materials in Jupiter's core operate according to the same principles that determine the properties of materials on Earth. Yet the extreme conditions within the planet create states of matter that cannot be achieved in terrestrial laboratories. Understanding how these quantum processes scale up to create the macroscopic properties we observe provides insights into fundamental physics that extend far beyond planetary science. The gravitational field that dominates Jupiter's environment operates according to Einstein's general theory of relativity, warping space-time in ways that affect everything from the trajectories of spacecraft to the orbital dynamics of the planet's many moons. Studying how gravity operates in Jupiter's environment provides tests of our understanding of fundamental physics under conditions that cannot be replicated on Earth. The electromagnetic phenomena that create Jupiter's powerful magnetic field and spectacular auroral displays operate according to Maxwell's equations, yet the scale and complexity of these phenomena push our understanding of electromagnetism to its limits. The planet's magnetosphere represents one of the largest and most complex electromagnetic structures in the solar system, providing a natural laboratory for studying plasma physics and electromagnetic field dynamics. The giant planet's story is still being written, and each new chapter reveals surprising plot twists that force us to reconsider our assumptions about how planetary systems work. As Jupiter continues its stately orbit around the Sun, carrying its extensive family of moons and maintaining its powerful magnetic field, it continues to influence the evolution of our solar system in ways both subtle and profound. As Jupiter continues its stately orbit around the Sun, its gravitational influence continues shaping our solar system's evolution. The planet's 12-year orbital period creates a cosmic clockwork that has been ticking for over 4 billion years, with each orbit bringing new configurations of gravitational forces that subtly alter the trajectories of countless smaller objects throughout the solar system. New moons may be captured as asteroids or comets venture too close to Jupiter's gravitational field and find themselves permanently trapped in orbit around the giant planet. These capture events continue today, adding new members to Jupiter's already extensive family of satellites and providing ongoing examples of how gravitational forces operate on cosmic scales. Asteroid orbits may be altered as objects in the main belt experience the accumulated effects of millions of gravitational interactions with Jupiter. These changes occur slowly, over timescales measured in millions of years, but they gradually reshape the distribution of material throughout the asteroid belt and influence the long-term evolution of the entire solar system. Comets may be redirected onto new paths as they venture inward from the distant Oort cloud and encounter Jupiter's massive gravitational field. Some may be captured into shorter period orbits that bring them regularly into the inner solar system, while others may be accelerated to such high velocities that they escape the solar system entirely, beginning journeys that will carry them to the stars. The massive scale that has defined Jupiter's role in our solar system for over 4 billion years will continue influencing our cosmic neighborhood for billions of years to come. The planet's gravitational field will continue to shepherd asteroids and comets, its magnetic field will continue to interact with the solar wind, and its atmospheric dynamics will continue to create some of the most spectacular weather phenomena in the solar system. Yet Jupiter itself is not static. The planet continues to evolve, albeit slowly by human standards. Its atmospheric patterns shift over timescales of decades and centuries. Its magnetic field changes on timescales ranging from years to millennia. Its internal structure continues to evolve as the planet slowly cools and contracts from its initial formation. These changes occur so slowly that they're difficult to detect within a human lifetime, but they represent ongoing processes that will ultimately transform Jupiter over geological time. Understanding how these processes operate provides insights into the long-term evolution of gas giants throughout the universe and helps us predict how planetary systems will change over cosmic time. Understanding Jupiter's true scale requires us to think beyond simple measurements and consider the planet's role in the grand symphony of gravitational, electromagnetic, and thermodynamic processes governing our solar system. The planet operates as a central node in a vast network of interactions that extends throughout our cosmic neighborhood and influences phenomena ranging from the aurora displays visible from Earth to the orbital dynamics of objects in the distant Kuiper belt. This network of interactions operates on multiple timescales simultaneously, creating a complex dynamic system that has maintained its basic structure for billions of years while continuously evolving in response to changing conditions. Understanding how this system works provides crucial insights into the fundamental principles that govern planetary system architecture and evolution throughout the universe. The gravitational processes that organize Jupiter's moon system into stable, resonant configurations operate according to the same principles that govern the formation and evolution of planetary systems around other stars. The electromagnetic processes that create Jupiter's powerful auroral displays provide insights into similar phenomena that may occur around gas giant exoplanets throughout the galaxy. The atmospheric dynamics that maintain Jupiter's distinctive banded structure and long-lived storm systems offer glimpses into the complex fluid mechanics that operate in the atmospheres of gas giants everywhere. Each aspect of Jupiter's behavior provides a piece of the puzzle that will eventually allow us to understand how gas giants form, evolve, and influence their environments throughout the universe. In its massive presence, we see reflected the fundamental forces shaping all cosmic structures from planetary systems to galaxies themselves. Jupiter embodies the remarkable ability of gravity to organize matter into complex hierarchical structures that span vast ranges of scale and exhibit rich dynamic behavior. The planet's internal structure, with its solid core, metallic hydrogen ocean, and gaseous atmosphere, represents a natural example of how matter organizes itself under extreme conditions. The gradients of pressure, temperature, and composition that exist within Jupiter's interior create environments that range from conditions similar to those found on rocky planets to exotic states of matter that exist nowhere else in the solar system. Jupiter's magnetosphere demonstrates how electromagnetic forces can organize charged particles into complex dynamic structures that span millions of miles and persist for billions of years. The radiation belts, plasmatori, and magnetic field lines that surround Jupiter represent some of the largest and most energetic structures in the solar system, yet they're created and maintained by the same electromagnetic processes that operate in much smaller systems. Jupiter's scale is ultimately a window into the universe's scale itself, reminding us we inhabit a cosmos where massive objects routinely influence their environments across distances and timescales, challenging human comprehension. The planet serves as a bridge between the familiar scales of human experience and the vast scales of cosmic phenomena, helping us understand how local processes connect to universal principles. When we study Jupiter's gravitational influence on its moons, we're learning about the same gravitational processes that organize star clusters and galactic structures. When we observe Jupiter's magnetic field interacting with the solar wind, we're witnessing electromagnetic processes that operate around stars and in the interstellar medium throughout the galaxy. When we analyze the complex chemistry occurring in Jupiter's atmosphere, we're studying processes that may be fundamental to the formation of organic molecules and the emergence of life throughout the universe. Jupiter's massive scale encompasses all of these phenomena, making it a laboratory for studying cosmic processes that operate across the entire range of scales found in nature. So there you have it. Jupiter transcends mere size. It defies even the most mind-bending concepts of massive scale. This extraordinary world represents far more than just the largest planet in our solar system. Jupiter stands as the cosmic architect that constructed the very solar system we call home, a gravitational mastermind whose influence has shaped every aspect of our cosmic neighborhood for over 4 billion years. Throughout our journey tonight, we've explored how Jupiter's massive scale operates across dimensions that challenge human comprehension. We've seen how the planet's physical size dwarfs everything else in our solar system, except the Sun itself, how its mass concentration creates gravitational effects that reach across billions of miles, and how its electromagnetic phenomena generate some of the most powerful and spectacular displays in our cosmic neighborhood. We've discovered that Jupiter's formation involved processes so violent and chaotic that they fundamentally altered the internal structure of the planet, creating a diffuse, fuzzy core that extends across nearly half the planet's radius. We've learned that the planet's rapid rotation and internal heat sources drive atmospheric dynamics that operate on scales and timescales that have no equivalent on Earth. We've explored how Jupiter's powerful magnetic field creates one of the largest and most complex electromagnetic structures in our solar system, trapping charged particles in radiation belts that make the space around Jupiter one of the most dangerous environments for both spacecraft and any potential future human explorers. We've seen how Jupiter's gravitational influence extends throughout our solar system, shepherding asteroids and comets, protecting the inner planets from potentially catastrophic impacts, and maintaining the delicate orbital relationships that keep our cosmic neighborhood stable over geological time. we've learned that Jupiter's role in our solar system's formation may have been crucial for the development of life on Earth, helping to deliver water to our planet during the early bombardment period, while preventing the formation of additional planets that might have destabilized the inner solar system. Most remarkably, we've discovered that Jupiter continues to surprise us with each new mission and observation, revealing complexities and phenomena that force us to continually revise our understanding of how gas giants form, evolve, and influence their environments. Every water droplet in our oceans, every breath of air in our atmosphere, every delicate condition allowing life to flourish on our pale blue dot exists because a giant world spinning in the outer darkness has been conducting a gravitational symphony for over 4 billion years. The water that makes up 70% of our planet's surface may have reached Earth because Jupiter's gravity scattered water-rich comets and asteroids throughout the inner solar system during our planet's early formation. The stable climate that has allowed life to evolve and thrive on Earth depends on our planet maintaining a stable orbit in the habitable zone around our Sun. This stability exists partly because Jupiter's massive gravitational field helps maintain the orbital relationships between the planets, preventing chaotic interactions that could send worlds careening into unstable orbits. The protection from catastrophic asteroid and comet impacts that has allowed complex life to develop over billions of years comes largely from Jupiter's role as a cosmic vacuum cleaner, capturing or deflecting many potentially dangerous objects before they can reach the inner solar system. Even the chemical elements that make up our bodies, the carbon, oxygen, nitrogen, and heavier elements forged in the nuclear furnaces of ancient stars, may have been delivered to Earth through processes influenced by Jupiter's gravitational stirring of the early solar system. Tonight, when you glimpse that wandering star moving slowly against the background of fixed light points, remember you're not simply observing another planet. You're witnessing the reason we exist at all, a cosmic guardian whose massive presence has shaped our solar system's architecture and maintained the delicate balance that makes life possible on our small, blue world. Jupiter's story is ultimately our story. The story of how gravity, electromagnetism, and thermodynamics can conspire to create complexity and beauty on scales that span from the quantum realm to the cosmic. In Jupiter's massive presence, we see reflected the fundamental forces that govern the universe itself, operating across scales that challenge our imagination, while following physical laws that we're only beginning to understand. As we continue to explore Jupiter with increasingly sophisticated instruments and send new missions to study its moons and magnetosphere, we're not just learning about one remarkable planet. We're uncovering principles that apply to gas giants throughout the galaxy, gaining insights that will help us understand the thousands of exoplanets being discovered around other stars, and perhaps even finding clues about the possibility of life in the subsurface oceans of Jupiter's moons. The massive scale of Jupiter reminds us that we live in a universe where the impossible becomes routine, where single objects can influence entire solar systems, and where the interplay of fundamental forces creates structures of breathtaking complexity and beauty. In contemplating Jupiter's true scale, we're really contemplating our place in a cosmos filled with wonders that exceed our wildest imaginations. I wish you a wonderful night. I hope you enjoyed this incredible journey with me here at Boring Science, exploring the massive scale of Jupiter and discovering how this extraordinary world has shaped our entire cosmic neighborhood. The universe is filled with remarkable objects and phenomena, but few capture the imagination quite like Jupiter, a failed star that became the guardian of our solar system. I'll see you tomorrow, as always, ready to explore more of the amazing discoveries that science reveals about our universe. There's always more to learn, more to discover, and more reasons to marvel at the incredible cosmos